Hello, this is Steve Groven, and the topic today is gravity and motion. Let me start off by asking you a question. If Wile E. Coyote and the Roadrunner fall off the cliff at the same time, who's going to hit the ground first? Roadrunner or Coyote? Let me answer this question by introducing you to a man named Galileo Galilei. Now, Galileo started his education in the church, and after that he moved on to medical school, but finally found his calling in mathematics. Now, in addition to mathematics, Galileo Galilei was an accomplished inventor. He invented the thermoscope, for example, which is a precursor to the thermometer. He also invented the telescope, or rather perfected the spyglass. He determined the law of the pendulum, and he was also known for throwing rocks off the Tower of Pisa. Now, at the time, common logic dictated that the heavier rock should hit the ground first because of the greater gravitational force acting on it. As it turned out, this was wrong, a point demonstrated by Galileo. You see, while it is true that the heavier rock will experience greater gravitational pull, both rocks experience the same gravitational acceleration. In fact, all objects on Earth or any planetary body experience the gravitational acceleration that is unique to that planetary body. Okay, for example, on Earth, the gravitational acceleration is 9.81 meters per second. If you're taking notes, now would be a good time to pause me. Okay, so let me explain how this works. Now, let's say you drop an object. Exactly 1 second after you drop that object, it's going to drop about 4.9 meters, which is going to bring its velocity up to 9.8 meters per second down. After the second second, it's going to drop another 14.7 meters, which is going to bring the velocity up to 19.6 meters per second downward, and on and on. So every 3 seconds, the rock is going to drop another 9.8 meter. Every 3 seconds, or every second, the speed is going to increase by 9.8 meters per second. That's where I'm bringing you the formula for velocity. Delta V is equal to G times T, where delta V means the change in velocity, the final velocity minus the initial velocity, and G is equal to the gravitational constant for that planetary body. Now, as already stated, Earth has a gravitational constant of 9.81 meters per second squared. The Moon, by contrast, has only 1.6 meters per second squared for the gravitational acceleration. Mars, our planet's closest cousin in our solar system, is 3.77 meters per second squared. And the largest planetary body in our solar system, Jupiter, is 23.6 meters per second squared. So what about the Sun? The Sun's gravitational constant is 274 meters per second squared. Okay, so all objects on Earth are going to fall at the same rate. So my next question is, how does this explain feathers? So when you drop a feather, contrary to the Earth's gravitational acceleration, feathers will fall gently to the Earth. So what's going on? It turns out that the feather, in addition to experiencing Earth's gravity, is experiencing an opposing force due to the Earth's atmosphere called air resistance. And air resistance is it's the friction due to the friction that any object moving through the atmosphere will feel due to moving, through the atmosphere. Okay, so let me show you how this works with this diagram here. Now, in the diagram, as the apple is falling, it is experiencing a force, or the force of gravity is pulling the apple down, but at the same time, air resistance is pushing up against the apple. The friction of the air is slowing it down. So the net force of the apple is going to be less or it's going to be in addition of the force of gravity and the force of resistance. Now, it's this effective air resistance that skydivers use in order to slow their fall. Now, you notice in the picture all the skydivers are kind of in a prone position, which is presenting the greatest possible area to the Earth's to the atmosphere. What that's going to do is going to bring them down at their terminal velocity. What terminal velocity is, it's a constant velocity at which the upward force of air is going to be equal to the downward force of gravity, which means they will not be accelerating. Now, the trick, of course, for skydivers is to increase their area in order to reduce the terminal velocity to a survivable, well, speed. So that is why they deploy parachutes. The parachute is going to increase the surface area of the parachutist, which will slow down the velocity. Okay, now another point about parachutists or skydivers. I've heard the term free fall used in conjunction with parachutists, but they're not exactly in free fall. The definition of free fall is any motion of a body where its weight is the only force acting on it, and any object on Earth is going to be subject to air resistance. So even if you're falling through the air resistance is going to be pushing back up on you. So let's see how this is going to work. The only way that you can experience free fall is if you are in a complete vacuum. Okay, so let's take a look at this picture of Karen Nyberg, a University of North Dakota graduate who has, who is an astronaut. Okay, so as you notice in the picture, Karen Nyberg's hair is kind of floating up. Okay, the reason why it's floating up is because she's in the space shuttle, which is currently in free fall. Now, let's see, how can I explain this? Let's say you're on a trampoline. You jump up and you fall down. But see, as you jump up from the trampoline, at that point at which your body reaches the highest altitude, you're going to experience just an instant of free fall or an instant of weightlessness. The reason being that right at that top of the arc, your velocity is changing from going upward to going downward. At that point, your velocity is exactly zero. So in a way, when you're jumping on the trampoline, you are experiencing a free fall. Karen Nyberg's hair, of course, is experiencing free fall and is floating up in kind of an interesting fashion. So how did they get into this point where they are experiencing free fall? I mean, they're not actually crashing into the atmosphere, so what's happening? What's happening is that the shuttle has gone into an orbit around the Earth. So we shoot the shuttle up into space, and the shuttle is actually going in a forward direction away from the Earth. Now, if you notice by the little orange dotted line, the shuttle wants to go straight. However, the force of gravity is pulling the shuttle down. Hold on, let me get a highlighter here. Okay, so it wants to go straight, but the force of gravity is pulling the shuttle down, which instead of letting the shuttle go straight, go in a straight path, which is what it wants to do, it causes the shuttle to go in the curved path around the Earth. This effect is called centripetal force. Centripetal force is what's pulling the shuttle around in a circular orbit around the Earth. Okay, some other interesting effects of free fall. Now, everybody knows that water runs downhill, but up in the shuttle, water is experiencing the same effect as free fall as Karen Nyberg's hair is. So in this picture of Clayton Anderson, the globular water that you're seeing is just, it's just that. It is water that is in free fall. So since there is no force of, since it's weightless, the force of gravity, well, down here on Earth, you see water running, but up there in space, water is the cohesive forces of the water is going to pull it together in a ball. Okay, so that's what happens to orbits. That's what happens to bodies in orbit around the Earth. So what happens on the Earth itself? Okay, so let's talk about projectile motion. Now, as you can see from this picture of the waterfall, as the water is shooting out, it is going in kind of a curved path. Let me highlight that again. So the water coming through the faucet is going up as far as it can. Once it hits the top of the arc, it goes back down straight towards Earth, and it is forming an arc. Now we call that a parabola. So let's see what kind of forces are actually acting on it. Let's take another instance. Let's say we have a volcano. Okay, now the volcano is shooting out lava bombs. In the volcano, there are going to be two components to there are two force components. There is a vertical force component going up, but there's also, if it's being shot out of the volcano at an angle, a horizontal component. So at the same time, while the lava bomb is going up due to the force forcing it out of the volcano, as it's going up in its arc, the force of gravity is pulling it back to Earth. So at some point, that lava bomb is going to start dropping back towards the Earth. Now, at the same time, it's still moving along its horizontal component, which is why eventually it is going to be pulled down, but at a greater distance away from the volcano from where it started. So the lava bomb is going to go in a parabola, an arc. Okay, now other objects, such as a baseball, follow the same law. Like, for example, the pitcher, when they throw the baseball, it is going to go in an arc. There's going to be a horizontal component and a vertical component. As soon as the ball leaves the pitcher's hand, the gravity is going to take over and start pulling it down. However, the horizontal velocity is going to continue on in its forward direction towards home plate. And basically, this is the definition of projectile motion. It's going to be a curved path an object will follow when it is thrown or propelled near the surface of the Earth. Okay, and that is actually all I have today. Thanks for listening. Give me a second. Okay, like I said, thank you for listening.